God, thank you so much, David. That was another thing on my list, but I forgot to do it. So great. So we are recording now, and wonderful. So we're gonna continue on our intermolecular forces worksheet, and I figured out how to make my camera not mirror, so I won't see what's backwards. We're just gonna go this way. And all right. Picking up where we left off last time. Okay. So you still see that right, like in the right way, right? Yes, I'm definitely putting the modules up. I just had to take them down for the quiz. I promise everything will be back to normal. Okay. So great, wonderful. So we left off here. We talked about London dispersion forces, which are weak forces, right, of attraction due to temporary asymmetries in electron density. And then we talked about when there's a permanent asymmetry in electron density where we can actually draw a dipole arrow, and then for the whole molecule, then the negative end, right, the partially negative end can attract to the partially positive end of the other molecule. Sorry, no, it's okay, Katie. And then, so then the water molecules, right, that's an example. And so water definitely displays dipole-dipole interactions. Okay. And so we have, what's another one? Another molecule that we've written so far over here that not only displays London dispersion forces, but also dipole-dipole. Mm-hmm. Yeah. Yeah, good. NF3 is another one that can display dipole-dipole forces. What I want to use though, I'm going to use NH3 because then we can also use that to illustrate the next intermolecular force for hydrogen bonding. So I'd like to use NH3. So does NH3, let's see, let's draw the Lewis structure for NH3. And actually, this is the perspective drawing. I'm showing it right with the wedge in the dash to show perspective, how that is a trigonal pyramidal shape, right? And is NH3, is that a polar molecule? Is there enough of an electronegativity difference between the nitrogen and the hydrogen there? Right. So nitrogen electronegativity 3.0, hydrogen 2.1, right? So that's a 0.9 electronegativity difference. So yeah, those bonds are polar, and the overall shape of the molecule lets us see that there is a side of the molecule with more electron density than the other side, and so that means then it is a polar molecule. Partial negative when there's more electron density on one side, and partial positive when there's less electron density, because nitrogen is more electronegative. So it pulls the electron density toward it. So we can draw that overall dipole for the molecule, and so that means it's going to be able to attract to another molecule of itself via dipole-dipole forces. Yeah. Yep, still pulls toward the nitrogen, which is more electronegative. That's what that means, right? Since nitrogen is more electronegative, it's got more electron density toward it, right? And so that attraction then between molecules, right, we call this the dipole-dipole force, right? The dipole-dipole, meaning two poles in this molecule attract to, right, the positive pole in this molecule attracts to the negative pole in that molecule. Yep, nitrogen has is more electronegative, exactly. Questions on dipole-dipole? Okay, you can just let me know when you have a question. What question do you have if you have one? Because nitrogen is more electronegative than hydrogen, right? We just showed this chart over here, the same chart that you're using every time when you're asked about polarity, right? So nitrogen is more electronegative than hydrogen. 2.1 for hydrogen, 3.0 for nitrogen. So it's more electronegative, meaning it pulls electron density toward it. So that means then the molecule has a partial negative side and a partial positive side. Is that okay? Okay. I'm not exactly sure. I'm not exactly sure how they found them. I read it a while ago and I don't remember to tell you enough right now. Thank you for asking. Why do we draw them twice like that? Because we have to show the interaction between at least two molecules, right? It's not a dipole-dipole force, right? Which is an intermolecular force if we only have one molecule, right? Intermolecular means between molecules. Between molecules. So we at least have to draw two. In reality, of course, there's way more than that, right? But we have to show at least two. They're not bonding. Are they bonding? Whoa, 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 careful there. Hold the phone. Are they bonding? Are these bonds? Like, is there a bond between each ammonia molecule here? Let's be careful. Right. They're attracting. Good. Thank you. So they're attracting, right? The better term for this is an attraction. Thank you. Be careful. It's constant. I'll be correcting people the whole semester. They'll say bonds a lot, but they mean attraction. All good, all good. All right. So clearing that up. It was a teaching moment, a learning moment. All right. So let's see. Now we have hydrogen bonding, which is the strongest intermolecular force. And so what happens is when hydrogens are covalently bonded to a nitrogen, oxygen, or fluorine, those sorry, I'm grabbing something else, okay? Those hydrogens, so hydrogens, covalently bonded to an N, O, or F. So do you notice these? What do you notice about these elements in terms of electronegativity? Are they highly electronegative or not very electronegative? Yeah, high or low? Yeah. Exactly, right? Those are some of, like, fluorine is the most electronegative, right? Then oxygen, then nitrogen. And so whenever a hydrogen, whenever a hydrogen is covalently bonded to one of those elements, that means then it's a very, very polar bond, right? And that means then that there's like an extra separation of electron density between a hydrogen, which is very not electronegative, right? Not electronegative, and the oxygen, nitrogen, or fluorine that is very electronegative. So let me show you how we draw this here. So say we've got a water molecule. All right, two lone pairs. And what we mean here is that, right, this oxygen, right, is really electronegative. So it's really pulling a lot of electron density away from the hydrogen. Because hydrogen is really not very electronegative. So it's like, ooh, it's like, oh, this hydrogen's really weak. So the oxygen's able to like pull even more electron density from it than like it would if it was a carbon, which would fight back a little bit. But hydrogen's really weak, and so this oxygen's able to like be greedy for electrons more than if it were another atom over here. And so that means then that this hydrogen is super partially positive. So super greedy. And super weak. All right, super electropositive. Okay. But since it's super partially positive, that means then it can attract to via the electrostatic force, right? It can attract to any other nitrogen, oxygen, or fluorine in another molecule. So that's what we mean here. Hydrogens that are covalently bonded to a nitrogen, oxygen, or fluorine are electrostatically attracted to any other nitrogen, oxygen, or fluorine. So an electrostatic attraction just means partial positive to partial negative. So hydrogen bonding just involves an attraction, right, between the partial positive hydrogen when it's bonded to an NOF and the partial negative oxygen or another nitrogen or fluorine. We can draw the other hydrogen bonding with a dashed line here. That's a hydrogen bond to an oxygen, right, in another water molecule. Right, partially negative here, very partially negative, we'll say, and very partially positive. So when they're very partially positive and very partially negative, then we can see this attraction. It's like a special type of dipole attraction between permanent dipoles when there's a hydrogen bonded to an N, O, or F. Yeah. So what you can do, everyone, to like make sure that you remember, and like I don't necessarily want to see this on your work that you're going to hand in. I wouldn't take off if you did, but this is like for your own notes to remember that this is not a true bond, but just an attraction. But when I say just an attraction, it's the most important intermolecular force in like on this planet. But I mean, it's just an attraction in that it's not a true bond. It's an electrostatic attraction. So let's make sure that we say that here. So we'll say an attraction not a bond. Right? I hear you. Right. The electrons aren't being shared between. It's just an electrostatic attraction, positive and negative, right? Poles of a magnet. Right? Just like electrons are attracted to protons in the nucleus, negative, positive, right? So here's a partial positive attracting to a partial negative, only just like a magnets. Okay. So each oxygen can accept 2 hydrogen bonds You can think of it as like the two lone pairs providing a negative area for a hydrogen to attract to. So 2 hydrogen bonds for each oxygen. And let's do it. So I wanted to use ammonia over here, NH3, to show you the hydrogen bonding for NH3 too. So here is ammonia again. I'm not showing the wedge in the dash, but I'm kind of showing the way that it exists where, right, it's in a little pyramidal shape. It's already posted, the key's already posted, right? And so that means then we can see a hydrogen bond, right, between this hydrogen. So can this hydrogen bond, is it attached to an N, O, or F? Right. This hydrogen is covalently bonded to an N, O, or F. So that means then it can attract, right, via electrostatic force to another N, O, or F. But it's an attraction, not a true bond. We could draw another one over here for water, right, to illustrate that each can accept 2 hydrogen bonds. Here's an HO, H over here again, right? And it goes on and on and on. So what about this one over here? What about this molecule? What about methanol? Let's see. Here, Y to the H. Well, what other atom would it be able to in water? Would O attract to O? What clumps, George? What clumps? Right. O wouldn't attract to O. Oxygen wouldn't attract to oxygen because that would repel. Look at what it says, Aberlinda. It doesn't say 2 bonds. It says 2 hydrogen bonds, right? 2 hydrogen bonds. Yeah, it already has 2 bonds like every other water molecule, but the hydrogen bonds, it can attract hydrogens. Hydrogen bond. Right. H bond is the same thing as H attraction. If I had my way, we would call it hydrogen attraction. We wouldn't call it hydrogen bond. It just makes people confused. That is not a true bond. It's just an attraction. Yeah. All right. So what about this molecule down here? How many hydrogens? Type in your answer. How many hydrogens can hydrogen bond on this molecule here? All right, so Haley, Yaned, and David win for the day. They all said 1, right? Most other people are saying 4. So what did we say though? Is this hydrogen covalently bonded to a nitrogen, oxygen, or fluorine? Right? Are these hydrogens here bonded to N, O, or F? No, they're not. So how many hydrogens can hydrogen bond in this molecule? Yeah. Okay. Thanks. Nice work. That's true. Okay. So we have to make sure that only hydrogens covalently bonded to an N or F, right, can be electrostatically attracted to any other N, O, or F because it has to be a polar bond. Not just any polar bond, but a very polar bond containing an H bonded to an N, an O to an H, or an F to an H. So these cannot hydrogen bond because they're bonded to carbon, and that's a nonpolar bond, right? There is no electron density separation here for the nonpolar bonds, right? So we could see this hydrogen bonding to the oxygen in another molecule. Must be present, NO or F must be present, but more than that, there has to be a hydrogen bonded to the NO or F. Like covalently bonded, right? These are not covalently bonded to NO or F, and this one is. All right, so here is a picture that's super cool. So like I said, hydrogen bonding is the most important intermolecular force because it holds together so many things, such as your very DNA. The DNA in the double helix that we see, right, in the nucleus of every cell in your body, except for red blood cells, right, has this double helical structure, and the only thing that's holding together the two helices is hydrogen bonding between molecules. These little lines here are showing hydrogen bonding, those little red lines there, and they're shown over here too, right? A hydrogen bonding to a nitrogen, a hydrogen bonding to an oxygen, right? And so forth. Okay, so even just the two helices are only held together by hydrogen bonding, not even covalent bonds, but hydrogen bonds. Let's see. Hydrogen bonding also holds together the proteins in your body, globular proteins such as hemoglobin, structural proteins such as alpha keratin in your hair and skin and nails. Hydrogen bonding is also responsible for the mechanism in your cell that, right, so here's hydrogen bonding between different strands of a protein. There's hydrogen bonding, right? Over here, it's showing, this is like a picture of a protein, kind of just stylized, right? But it's also showing hydrogen bonding, right, between different parts of a protein. And so there you go. So the UV rays, like, yeah, that probably has to do with the hydrogen bonds too, but UV rays also are strong enough to rip electrons off of atoms, and when that happens, no longer can the bond be maintained between atoms. And so maybe, I mean, I don't know for sure about the hydrogen bonds. I guess that they would be disrupted due to like increased vibrations from UV exposure, but also it's more than that. It's actually the electrons get ripped off of the structure and interfere therefore with the bonds, the actual covalent bonds in DNA. All right. So here's something to think about. The stronger the intermolecular forces, that means then the tighter the molecules are held together, and therefore the more energy that it takes to disrupt those forces holding those molecules together. So yeah, also size has to do with this too, where if they have the same intermolecular forces, the larger one is going to be more attracted to each other. The larger molecules will be, because they're going to have more opportunity for London dispersion forces. So the larger the surface area of the molecule, the more opportunity for London dispersion forces. And so the more tightly the molecules are able to be attracted to each other, the more strong their attractions, the more energy it requires to disrupt those attractions, right? So boiling point will be higher in a molecule that has stronger intermolecular forces. Boiling point will also be higher in molecules that are larger, due to the fact that they have more surface area and more opportunity for that London dispersion force to occur. Okay, so I want to talk to you about a different topic right now. So we're going to go to the board. It's a different topic in that it's like in a different section, but it's very related to this, and so it's a good time to bring it up. Okay. So we're going to talk about why oil and water don't mix in terms of solubility. Cool, you're welcome, thank you. And so let's talk about that. Remember, your exam 2 is on April 7th. I don't know how we're going to do it. If we're together again by that time, we'll have it in person. If not, then we'll have it online. And so, yeah, so talking about solubility in terms of intermolecular forces. Okay. Intermolecular forces and solubility. So the question is, why don't oil and water mix? Right? We've maybe have come into, have this experience, maybe with salad dressing is one, where you have to shake, balsamic vinaigrette or whatever vinaigrette salad dressing because it separates, right? We notice that there's 2 layers if we don't shake, a salad dressing in a while. That's because oil and water don't mix, and you've probably heard this over and over, right? So now we can think about it in terms of, on that atomic level where it's all about the intermolecular forces. And so what is water? Is water polar or non-polar? Good. I'm seeing lots of people say polar. That's true, right? So answer, water is polar. So that means it's got hydrogen bonding and dipole-dipole. Intermolecular forces, right? Which attract the molecules together like magnets. right? Whereas oil is nonpolar. Right? So that means then water kind of pushes the oil out because the water molecules attract to each other like magnets, but oil is nonpolar, so it doesn't have that sort of attraction between molecules, right? The positive and negative poles that water does. And so it's non-magnetic. We can think of oil molecules as being non-magnetic. So water pushes the oil out. Water excludes the oil. All right, so I'm going to share my screen. Does everyone have this? So I can show you what we mean by that, magnets. Okay, so I'm going to share my screen. I'll show it again in a second. Okay, so over here, right, you're all seeing this? Okay, so here, right, is a figure showing what we mean by this, right? These are the magnetic marbles on the side here. Do you remember, Mark? I used to have those when I was a kid. And these are magnetic, so they attract to each other. Once you get non-magnetic marbles in there, oh, you see the, really? You really see the diagram? Oh my God, okay. Here? Ay, ay, ay. Okay, hold on. Okay, so, all right, so here are the magnetic marbles attracting to each other, right? And as soon as a non-magnetic marble gets in there, these aren't going to want to include the non-magnetic marbles, right? They're not able to attract to the magnets. So the magnetic marbles are going to push out and exclude the non-magnetic ones. And that is a really good analogy for why oil and water don't mix. Because water is polar. We see it on this, this figure down here, the molecular art, right, of water molecules, H2O. And then here is up here hexane, which is just carbon and hydrogen. So oil is a lot like hexane, is that there's a lot of carbon and hydrogen only. And so then when you add something that's non-polar, right, to water, and it's going to be less dense because the particles aren't as attracted to each other, so they're not as packed together, it's going to float on top. It's going to form two separate layers. So the water molecules here, even if you shake it, over time, those non-polar molecules are going to be excluded from the water, because water you can think of as magnetic and the oil is like non-magnetic. So how is that? Okay, so I meant to post that on your module. It should be there. I went to go do it and then I got distracted. So I'm gonna make sure it is. And if it's not, I'll post it, okay? So now we can arrive at this very important concept as well. Everyone good here? Dun, 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 like dissolves like. Like dissolves like. So this is very important in terms of solubility, in terms of not just in chemistry, but like everyday life, things that we notice. Okay. So what this means is that polar molecules and polar molecules do mix together. Right? So polar molecules mix together. They are soluble. Right? Nonpolar and nonpolar, so like dissolves like. So polar and polar, when they're alike, they dissolve in each other. When they're also nonpolar, so nonpolar and nonpolar also dissolve in each other. Right? They are soluble, right? They dissolve. But whenever we get polar plus nonpolar, that's not like each other, and so therefore they don't mix together. So that is why oil and water do not mix. Because of like dissolves like, and because of the magnetic thing we were talking about. Cool, I haven't been seeing the comments. I'm glad you're having fun. Okay, so let's do a demonstration. So I don't have safety glasses, okay? I don't have safety glasses, but can I show you anyway? I don't have safety glasses, but please, okay, just, okay. So the question is, so if for this demonstration, so I'm gonna erase this now. Like dissolves like. All right, so in this test tube here, I've got hexane. Hexane, which is like the molecule that we just saw. If only it were like that. So this is hexane. This is in this bottle here. I poured it earlier. Hexane is just carbon and hydrogen. So hexane, carbon and hydrogen only. And we've got it in a test tube. Okay, so hexane. C6H14. So only carbon and hydrogen. So is hexane polar or nonpolar? Yeah, just carbon and hydrogen. Hopefully we're getting used to seeing that carbon and hydrogen, that bond is not polar, right? So nonpolar. And you said water was polar, right? Okay, so the question is, are they going to mix together? If I put one on top of the other and I shake it around, are they going to mix? Right, they're not going to mix. Okay, let's see if that's true. I've got my sink right over here. Do you see the two distinct layers there? Even if I shake them up? They look like they're mixing, but we see the layers separate. Two distinct layers. All right. So now the question is, which layer will iodine dissolve in? Oh, sorry. Which layer will I2 dissolve in? That's a good question. That's the question to ask. Did we say, Natalie, careful, did we say that nonpolar molecules don't dissolve? Or did we say that they dissolve with other nonpolar molecules, right? Okay, so I'm getting like half and half, maybe a little more hexane. So yeah, the question is I2 polar or nonpolar? Is there a separation of electron density for I2? Right, I2 looks like this. So is there a separation of electron density there? No, right? So it's nonpolar. So that means which layer will it dissolve in? If I2 is nonpolar, which layer will it dissolve in? The hexane or the water? Okay, cool. So good, we're getting a lot more hexane answers here. So I've got iodine here, little chips. It kind of looks metallic, but it's not. It's not a metal, right? It's a non-metal. Okay, I'm gonna shake it up. All right. So which layer did it dissolve in? Yeah, right? We saw in that little, on the picture that was below the magnetic marbles, right? That hexane or other oil, right? Oil floats on water, like you see an oil skim on a puddle, right? Or if like you take a bath with oil, you see it kind of like pooling at the top, right? Essential oils are less dense than water, so they pool at the top too. Hex insane, love it, love it, love it. Awesome. So that is one of the prettiest colors in chemistry. I would say I love that color. It looks even prettier with the sun coming in behind it. So yeah, the iodine, when dissolved in hexane, turns that beautiful fuchsia color. So yeah, that's what was happening, right? So we've got the two layers. We've got the water layer where there's water molecules, right? Hydrogen bonding to each other. Right. And they're so magnetically attracted to one another that they're not going to let something that's nonpolar in, right? Because it's not magnetic. And so here's the hexane, right? And then I'll draw the iodine in the purple color, right? So there's just, so what's the intermolecular force that allows hexane and iodine to mix together? What intermolecular force allows iodine and hexane to mix together? What intermolecular force allows iodine and hexane to mix together? Okay, well, people that are saying hydrogen bonding, what did we say about hydrogen bonding? What has to be present in the molecule for a hydrogen bond? Right here. Are those molecules polar? And in addition, do they have an NH, OH, or FH? And if they're nonpolar, like we said, do they have dipole-dipole? Right? So they're nonpolar. So what's the only intermolecular force that exists for nonpolar molecules? London dispersion, right? London dispersion is the only intermolecular force that exists for nonpolar molecules, right? So like these ones down here, nonpolar, right? So let's add I2 and hexane to our list of nonpolar molecules that can have London dispersion. Yeah, only London dispersion. So they're nonpolar, so only London dispersion. I know I told you that hydrogen bonding was the most important, and it's the one I love the most, but it doesn't occur with nonpolar molecules. Okay, so London dispersion. Like dissolves like. Okay. Questions here? Here? It's just I, and then here's an HOH for water. That's an HOH for water, showing the hydrogen of water, hydrogen bonding to the oxygen. Here? C6, yeah, C6H14. Thank you. Cool. All right, so that is like dissolves like. So thinking about polar molecules, magnets holding together, being able to attract and dissolve in each other. Non-polar, though, can't dissolve in polar, but they can dissolve together because they still do have intermolecular forces together, just not as strong as the magnet polar molecules do. So we're going to switch gears again and talk about balancing. We're going to talk about chemical reactions. So up until this point, we really haven't talked about specific chemical reactions. So I'm going to start now, and we're going to talk about balancing chemical reactions first. And I know we said that there'd be another worksheet for today, but the stoichiometry worksheet that I mentioned in an earlier email needing it for today, we're not going to get to it today, but we will get to it next time. So this worksheet will be saved for next time. The mass-to-mass calculations using stoichiometry. So the stoichiometry worksheet is in week 8, so make sure that's printed for next time. And so chemical reactions occur, and when they do, we often see evidences of chemical reactions. What are some pieces of evidence that we see in chemical reactions that you've seen like in lab so far this semester? Okay, so energy release, color change, gas formation, yep, temperature, yep, so releasing energy, change in temperature, gas formation. Light is another form of energy that can be released from a chemical reaction that we know it's happening. Gas, there's one that people haven't said, precipitation, precipitation. Condensation is actually a physical change, right? Condensation is just the changing from gas to liquid, something condensing. But precipitate formation. So we're going to talk about those things. Before we do that, though, we're going to learn how to balance chemical equations, because that's really important to be able to account for everything that's going on in a chemical reaction. So let me show you. I'm going to share my screen real quick. Yeah, nice work on all those there. So, oops, you probably can't see that. Hold on. Okay. So we can see that. You don't have to tell me. I think I know you can. Okay. So chat, okay, come on. Jeez. Get away. You're not going away. Oh my God. Oh, hold on. Okay. Okay. Whatever. Okay, so I'm not gonna see your chat for a minute. Can you see chat right now? Can you see the chat? Can you all see the chat right now? Okay. Oh, you're down. Oh, you can't. Okay, so I'm gonna get rid of the chat box for now. Wires. Okay. And chemical reactions, when we write them out in the equation, we have to make sure that we balance the chemicals. We have to balance the equation so that mass is conserved. So when we write out chemical equations where we have the reactants on the left-hand side, right? You've got reactants over here. Wait, you can't see it, can you? Oh my goodness gracious. Hold on. Okay, thank you so much for being so participatory, but like, why? Okay, it's just going really slow. Right. Okay. But you can see this slide right here. Okay. Thank you. That's what I wanted to know. So this looks good. Okay, so when we write chemical reactions, we need to make sure that every atom is accounted for in the reactants on the left-hand side, right? And the products on the right-hand side. So this follows the law of conservation of mass, which just states that mass cannot be created or destroyed during a chemical reaction. And so that means then that we have to balance the chemical equation to account for all of the atoms, because atoms have mass, and so that's what we want to look for. So in this case, right, is mass conserved for this chemical equation? Right? Do we have the same number of atoms of carbon as we do on one side as the other side? Do we have the same number of oxygens on one side as the other side? Do we have the same number of hydrogens on one side as the other side? Right. Right. It's not conserved. So then what we can do, right, is balance the chemical equation so that all the atoms are conserved, meaning that they're saved. They're the same from the starting reactants, right, to the products over here, right? And so once we put a 2 out front of the oxygen, then that means then there's overall 4 oxygen atoms, 1, 2, 3, 4. And if we put a 2 out front over here in front of the water molecules, right, then all of a sudden that means that brings it up to 1, 2, 3, 4 oxygens as well on the right hand side, right, on the product side. And so in this way, we're able to balance out, right? We're able to save the number of atoms that we had in the beginning, right, in the end over here. So that's why we have to balance chemical reactions, chemical equations, because if not, then we would just be like getting matter out of thin air, but that can't happen, right? Matter, or rather mass, is not created or destroyed during a chemical reaction. It only gets transformed. So, great. Okay, so let's talk about that. So this is in chapter 4, chemical reactions. And you told me all of the pieces, all of the evidence that we have, right? The pieces of evidence that with the observations we can see when, or feel, or take the temperature of, right? Or smell. Odor is another one that we can say that is an evidence of a chemical reaction. So you told me all those great things. And then when we write the chemical equation, so for example, this is a chemical equation. So we just saw the methane one, right? So another chemical equation, another combustion reaction that we've done before, right, is the combustion of propanes. Remember when we exploded the balloon in the beginning of the semester? So propane, right, is C3H8, and let me just start over here, C3H8. And is propane a gas, a solid, a liquid, or is it aqueous? Yeah. Yeah, right, it was in the balloon, it blew up the balloon, so propane at room temperature is a gas, and so we put a little lowercase g after it in parentheses, because that's a really important part of a chemical equation as well, is to write out the phases of matter, right? Because that matters, right? It matters if something is a gas or liquid or solid. It just allows us to categorize everything that's going on in the reaction even more thoroughly, okay? So for combustion, what reacts with a fuel? For combustion, what do we need as a reactant as well? You're right that heat is involved, except heat is involved as a product because it's produced, right? Heat is produced, energy is produced, but what else is needed in order for the reaction to happen? Yeah, it's oxygen, exactly. O2, which is a gas, right? And so the reactants are on the left-hand side. Of the chemical equation, right? And the products are on the right-hand side. So the product of any combustion is going to be carbon dioxide, which is a gas. And what's the other product for any combustion? What did you see up on the screen for methane 2? Yep, C3H8 is propane. Yeah, H2O. And I'm going to write, instead of just heat, I'm going to write energy, because we saw light, which is a form of energy, and we can feel the heat. So in all, it's going to be energy. Right. So then the products are written on the right-hand side of the chemical equation. And is mass conserved the way we wrote it here? have we created, what I should say is, have we made sure that atoms are not created or destroyed? Is mass conserved? Is it balanced is another way to think of it. Right, it's not balanced, right? So we have to balance. Right, because of the law of conservation of mass. Mass is not created or destroyed. So we're going to balance in this order. First, we want to balance the metals in a chemical equation. Then we want to balance any non-metals. Then we want to balance any polyatomic ions in the equation. And then we want to balance hydrogens. Okay, and then finally we can balance oxygens. So when we go in this order, it just it helps us set a cognitive routine, right? But also what it does is it allows us, we'll see, like especially for combustion, it's a good order to go in because as I found, and as you'll see this order in different sources as well, I found that it just makes it easier going in this order here. Okay, so real quick, can we just balance this one together? I know it'll be like a couple minutes over, but I just want to make sure we get through this together to show you how to do it so you can start doing the homework. I'm going to be adding a bunch of balancing for the homework so you can practice with this as soon as possible. Thank you. Okay, so let's do this. Do we have any metals involved in this chemical equation here? Right, there's no metal, so we can do non-metals. What's the non-metal here that isn't hydrogen or oxygen? Because they get their own step. So what's the non-metal? Right, carbon is the only non-metal in here that isn't carbon or oxygen. I mean, isn't oxygen or hydrogen. So what you can do is start a tally, right? You can begin tallying up the number of atoms. And so how many carbons are there on the left hand on the reactant side? How many carbon on the reactant side? Yeah, there's 3 carbon on the reactant side. How many carbons on the product side? 1 carbon on the product side. So are we going to do this? Can we do this? Can I do that? Oops, excuse me, can I put a 3 there? I meant to put a 3. Can I put a 3 here? Right. That would change the chemical formula and it would make it a different molecule. So we can't change the little numbers down below, but we can use a coefficient. We can put a big number out front. It's a coefficient. And just like a coefficient in math, it applies to not only the carbon, but to the oxygen. So now there's 3 carbons on each side. Right. You mean a 3, right? Yeah, we had a 3 over here, exactly. A 3 in front here. All right. So then next, we don't have any polyatomic ions here, but and the reason that they get their own stuff is because you can keep the whole ion together. You don't want to break it up into the separate atoms. You can just keep the whole polyatomic ion together in one group, and that makes it a lot easier. For sure, but we're going to keep going, right? So now we can do hydrogens, right? So that's the next step here. So how many hydrogens are there on the reactant side? Right, there's 8 hydrogens here. How many are there on the product side? Great, everyone. There's 2 hydrogens over here. So what number can we place out front here to make it balance? Yeah. Yeah, we can use a 4. So 4 times 2, 4 times 2, right, is 8. So now there's 8 right there. 4 times 2. So this is multiplied there, right? And what about oxygen? How many oxygen are there on the left-hand side, on the reactant side? Right. There's 2 oxygens on the reactant side. Now, how many are there on the product side? How many oxygens on the product side? What do we think? Cool, so I'm seeing a mix, now I'm seeing 10s, okay, cool. So if you counted up 10, you were correct, because 3 times 2 is 6, right? 3 times 2 is 6, and 4 times 1 is 4. So 6 plus 4 is 10. Right, exactly. So there's 10 oxygens here. There's 2 over here, so what number do we put out front here? Yep, what number goes here? Awesome. Great, everybody. That's true, and now there are 10 oxygens. So now everything is accounted for. Now this chemical reaction is balanced, right? And that's how you want to do it. You want to go through and count lots of numbers and put coefficients out front. You're never going to make a change to the lower numbers down below, only the big numbers out front, because in that way you're just saying how many there are, not that you've changed the molecular formula. Okay, everyone, I'll leave this up for a minute, and thank you so much for staying 5 minutes. Oh my gosh, this is so great. So thank you. You're all awesome. You're doing great. I know it's stressful. I know it's a lot of different work, a lot of new work. So thank you so much. Enjoy your spring break. I know. I'll see you the week after, okay? So great. Bye, yeah, and I'll see you in lab in a little bit.